In the last section, we discussed electrons, lights, waves, and the properties of waves and electrons. Just to review, a wave is a vibrating disturbance through which energy is transmitted. And you can describe a wave through its amplitude, frequency, and the amplitude is basically the difference between the origin and the peak or the crest of a wave, or the origin and a trough. And the frequency is how many waves pass through a specific point in a second. The units of measurement for wavelength varies, and a wavelength is the distance from one peak of one wave to the next peak of the wave, or from one trough to the next. Wavelengths usually are measured in meters, centimeters, nanometers, angstroms, which an angstrom is basically equal to 10 to a negative 10th meters. Either way, the base unit is always a meter. That's just to review the basics of waves. Up until the 1900s, scientists believed that the energy of an electron acted like a wave, meaning that it was able to move up and down. An example of that motion was found in the electromagnetic radiation, so the EM radiation. And that's something that's all around us and takes many forms. Microwaves, X-rays, flame from a burning fire, all of those are examples of common electromagnetic radiations. The collection of all types of electromagnetic radiations is known as the electromagnetic spectrum, which we've all known and heard before. The electromagnetic spectrum has 7 parts: the radio waves, microwaves, IR waves, which are infrared waves, visible rays, UV rays, X-rays, gamma rays. And unfortunately, humans can only see one small part of that spectrum, and that's visible light spectrum. That's our rainbow colored portion. So red, orange, yellow, green, blue, indigo, violet, those are the colors that we can see. And from longest to shortest wavelengths in the visible light spectrum, we go from red, orange, yellow, green, blue, indigo, and then violet. So all of these waves in the electromagnetic spectrum have different lengths in meters. Some of the waves, like radio waves, can be the size of buildings, and some of the waves can be the size of atoms or atomic nuclei. The point being is that back then they thought that electrons acted like waves. However, we began to realize that it wasn't exactly how we used to think it was. Max Planck, he discovered that electrons can also act like particles. So not only did they act like waves, but they acted like particles, because when they hit a metal surface, they emitted electrons. Planck, he heated solids until they glowed red hot, and then observed that they emitted electromagnetic radiation. He found that electromagnetic radiation was emitted in small packages, and he called these packages quanta. A quantum, which is singular for quanta, is the smallest quantity of energy that can be emitted or absorbed in the form of electromagnetic energy. Planck measured the energy of a quantum with this equation: E equals h times nu. The Greek letter nu looks like a V in English, in the English alphabet. H is Planck's constant at 6.626 times 10 to a negative 34th joules per second, and the letter V, or nu, is the frequency of the light absorbed or emitted. Planck's constant relates the energy of one quantum of electromagnetic radiation to the frequency of that radiation. And just as a reminder, a joule is a SI unit of energy. Or, if you are using the speed of light, which is constant and denoted by a variable c, the equation for the quantum can look like E equals h, which is Planck's constant, times c, which is the speed of light, divided by lambda. Lambda is wavelength. And the reason why you can do that is because nu equals c over lambda. Quantum theory is a study of matter and energy on the atomic and subatomic levels. Quantum theory allows scientists to understand how electrons behave and to make predictions on that behavior. There are many scientists who contributed to quantum theory after Planck, including Albert Einstein. Albert Einstein took Planck's theory to the next level. He shot a beam of light onto a metal surface, which caused electrons to be emitted. This emission is called the photoelectric effect. Einstein found out that the number of electrons that were ejected from the metal were proportional to the brightness of the light. Therefore, the brighter the light, the more electrons were ejected. But just so you know, the energy of the light must be above a certain frequency, which we call the threshold frequency for electrons to be ejected. If the energy is below the threshold frequency, none of the electrons will be ejected. In other words, electrons inside metal atoms are held together pretty tightly, so it takes a lot of light to push an electron out. So if the light doesn't have enough frequency, then the electron will move. Einstein suggested that the beam of light that could eject an electron was a particle of light we call a proton. Einstein said that photons possess energy E, which is given by the equation E equals h times nu, or E equals h times c divided by lambda. So energy is equal to the wavelength multiplied by the frequency of light absorbed or emitted. And just remember, c equals 3 times 10 to the 8th power meters per second, which is the speed of light. This just means that a photon is a quantum. Photons are the smallest unit of energy, like a quantum, and have the following characteristics that you need to be aware of. Photons are neutral and stable and have no mass. They interact with electrons and have energy and speed that is dependent on their frequency. And they can travel at the speed of light, but only in vacuums, such as space. And all light and electromagnetic energy are made up of photons. Overall, this discovery from all of these scientists enabled quantum theory to be developed, which allows scientists to project and understand how electrons behave. And just a reminder, quantum theory explains the behavior of matter and energy on atomic and subatomic levels. One thing I do want to clarify is that photons are different from electrons, because photons are just the smallest unit of energy, like a quantum, whereas an electron is a subatomic particle of an atom with a negative charge and essentially massless. Electrons are one of the 3 subatomic particles that make up elements or atoms. And we have electrons, neutrons, protons, electrons with a negative charge, neutrons with a neutral charge, and protons with a positive charge. We have 118 known elements, and each one is unique, made up of one type of atom. Elements can have different numbers of protons and electrons, and that explains all the differences in the physical properties of matter. Elements can exist at different phases, so they're not always going to be solid at room temperature. Some of them might be liquid or solid, at room temperature. All of these 118 known elements, they're listed and organized in a chart that we call the periodic table. This was developed by Mr. Mendeleev, Dmitry Mendeleev, in 1869. The periodic table is arranged in a grid format, so each element sits in a specific place in the grid according to its atomic number. As you can see, the atomic numbers on the top left-hand side of the little boxes in the periodic table. These basically are the number of protons that an atom contains. So for hydrogen, we have 1 as the atomic number, meaning that we have 1 proton in hydrogen. In helium, you have 2, so that means we have 2 protons in helium. Lithium has 3, beryllium has 4, boron has 5, carbon has 6, and so on. The periodic table contains 3 major categories of elements. We have metals, which are positioned to the left side of the table, metalloids, which are in the middle, and nonmetals, which are positioned to the right. The periodic table is organized by rows and columns. A horizontal row, which goes from left to right or right to left, whichever way you would prefer, is called a period. A vertical column going up and down is called a group or a family. The structure of the table is based on mass. The elements are arranged from left to right by increasing atomic number. So as you go across from left to right, each element has 1 more electron and 1 more proton than the element to the left of it. Groups and families, which are the vertical columns in the periodic table, tend to have similar physical and chemical properties due to the valence electrons that they have. Speaking of valence electrons, the periodic table is governed by periodic law, which states that the physical and chemical properties of the elements recur in a systematic and predictable way when the elements are arranged in order of increasing atomic number. This is actually one of the most important concepts in chemistry, because this has allowed scientists, chemists, to predict how an element will behave. Basically, if you know an element's position on the periodic table, you can predict its properties, and that includes looking at its position in the periodic table and finding out how many valence electrons, or just using the periodic table to find out the electron configuration, and by just looking at that, you're able to see how it will react with other elements. Elements in the periodic table are basically split up into 3 categories: metals, nonmetals, and metalloids. We have metals, which are solid at room temperature, except for mercury, which is liquid at room temperature. And these metals are these are the properties of the metals. They're ductile, which means they can be pulled into thin wires. Metals are excellent and popular for computers. Excellent for making wires for computers, such as gold and aluminum. All of these things are metals, and they are ductile. Lustrous, so basically very shiny. Metals are pretty shiny. They're good conductors of electricity and heat. They are malleable, which means you can hammer them into small sheets like aluminum. And they are prone to losing electrons pretty easily. Nonmetals have the properties that are opposite from those of metals, which are the ones highlighted in blue in this periodic table. Nonmetals are brittle. They're dull, not shiny. So they're brittle, dull, not shiny. They're poor conductors of electricity and heat, and they can be solid, liquid, or gas at room temperature. And nonmetals are able to gain or share electrons pretty easily. The last category for elements is metalloids. Metalloids are this small group of elements in the middle right part of the periodic table. If you notice, it looks like a little ladder. They have properties that are a mix of metals and non-metal properties. So They are solid at room temperature. They can be dull or shiny. It honestly, you have a mix of good conductors and poor conductors of electricity and heat, and they're characterized by having physical properties and that tend to be metallic and chemical properties that tend to be non-metallic. So they're like hybrids